All right.
Great.
The last talk of the session and of the week will be given by Nikolas Breuckmann, and he'll talk about twisted product constructions for LDPC quantum codes.
Hi everyone. Thank you very much for the invitation. So my talk will deal about some recent developments in quantum error correction, and in particular I will talk about 3 different constructions of quantum codes using so-called twisted products. So let's start at the beginning. In 1995, Shor invented quantum codes in order to show that quantum errors can be corrected. And the overarching idea is that we can hide a quantum state in non-local degrees of freedom of a larger system, adding redundancy, which we can kind of use to protect our quantum information. And in order to correct errors, we can perform check measurements, which have to commute, of course, to infer information about the errors. But I will not talk too much about this process. I will just talk about quantum codes themselves. Okay, so quantum codes are parameterized by 3 important parameters. So first of all, the number of physical qubits, which we denote by n. Then there's the number of encoded qubits, so how much information we can encode in our quantum code, and a parameter which tells us how good we are protected against errors is called the distance. So this is the smallest weight of an undetectable error. Okay, so classical codes can be described simply by a so-called parity check matrix. So this is just a binary matrix with rows performing parity checks. And the kernel of this matrix is some subspace of all possible bit combinations. And this subspace we call a code. And similarly, we can describe certain types of quantum codes, so-called CSS quantum codes, by 2 parity check matrices, HX and HZ, where HX performs measurements against phase flip errors, and HZ performs measurements against bit flip errors. And I mentioned earlier that, of course, our observables have to commute, and this translates into the fact that these matrices have to multiply to 0, modulo 2, of course. And the reason why I will only talk about CSS codes in this talk is partially motivated by a result by Bravi, Lemos, and Terhal. And this result tells us that any stabilizer code, which is a larger family of quantum codes, can be mapped onto a CSS code. So we don't actually lose too much if we only care about the scaling of these parameters. So let's restrict ourselves a little bit more. The most reasonable codes, I would say, are so-called LDPC quantum codes, and there are 2 conditions. So first of all, I should say that this notion also exists in the classical world, and the definition is essentially the same. We demand that each check operates on a constant number of qubits or bits, and each bit or qubit should participate only in a constant number of checks. So in terms of these parity check matrices, these conditions just say that the parity check matrices of the classical code or of the CSS codes must be sparse. It turns out that that there are classical LDPC codes which are so-called good codes, and good has a very precise definition here. Good means that the number of encoded bits scales linearly with n, so the total number of bits, and the distance scales linearly in n. So this is like the best asymptotic scaling you can hope for. And this is even these codes are actually quite easy to get. So even if you just take a random parity check matrix which is sparse, with high probability, you will have a good code on your hands. And a big open question is, can LDPC quantum codes be good? It turns out that the single condition that our checks have to commute makes this question quite hard. So the intuition here is that, let's say we take, for hx, we take the parity check matrix of a good classical code. Then because of this condition, we see that the rows of the z checks, which have to be in the kernel of the x checks, cannot have low support, and therefore hz cannot be sparse. And to add insult to injury, until recently, it wasn't even clear whether we could have distances scaling beyond polylog n times square root of n. So for this, let me kind of just briefly recap the history of LDPC quantum codes with large distances. So first of all, there was Calligraphs toric code, which of course has distance scaling with the square root of n. Then there was, in 2002, a slight improvement, which is actually quite a complicated construction due to Friedman, Meyer, and Luo, which improves the distance scaling by the 4th root of a log, so not by very much. Then, of course, a lot of things happened. Great results were produced, but there wasn't much happening in terms of distance records. Until in 2020, a lot of stuff happened, partially because maybe a lot of people had a lot of time on their hands. So first of all, Eva, Kaufmann, and Seymour improved the polylog scaling by a square root of a log n. And then Kaufmann and Evra tweaked this construction a bit further 4 months after, and actually showed that it's possible to get arbitrary polylogs in front of the square root of n. But still, some people believed that there was a barrier, and it wasn't really clear whether this barrier can be broken until Hastings, Haar, and O'Donnell showed that actually there are codes which break this square root polylog barrier significantly by showing that there are codes with distance scaling as n to the 3/5 of the polylogs. Then again, shortly after, Panteleev and Kalachev introduced a different construction, but related construction. And they showed that actually they can get as close as they want to linearly scaling distance, so only up to a log factor. And then finally, like a week later, myself and my co-author, we showed that there is a third construction. And the difference to the first two is that the first two use randomness. So these parameters only hold with high probability, whereas for us, this result is unconditional. And there are also some extra nice features that I will talk about later. Okay, so just to kind of give you an idea of what this will be about. So there are product constructions which take two classical codes as inputs, and they produce a quantum code. And the nice thing is that the quantum code actually inherits properties of the input codes. And this goes under different names. So I will call this essentially the tensor product of two classical codes. So the algebraic approach is quite technical, and I try to avoid this in the interest of time and not having to introduce too many notions. So I will talk about this in terms of topology, and I hope then the results will be intuitive. So how do I talk about codes in terms of topology? So let me give you an example. Let's take a repetition code on 3 bits. So the code words, so this is just a classical code, the code words are just 0, 0, 0 and 1, 1, 1. And this code is defined by 3 parity checks, just checking the parity of the first 2, and then the second and the third, and the first and the third. And I can turn this into a picture of a circle by identifying the bits with the edges and the vertices with the checks. Okay, so I can turn the repetition code into just a cyclic graph. Okay, and now this product construction is can be simply understood as just a product of 2 cycles, and the product of 2 cycles is simply a torus. And this notion essentially linearizes. And in fact, the toric code, which you see on the right-hand side, you might be familiar with it, can be obtained as a product of two repetition codes. So I can express this in terms of matrices. So H1 is just the H1 and H2 are just the parity check matrices that I've shown you before. And you can convince yourself by doing the simple algebra that this, in fact, these two parity check matrices commute. But we make a following observation. Due to the Kronecker product that you see appearing here, the size of the quantum code is the product of the input code lengths. However, it turns out that the distance is just the same as for the input codes. And what this tells us is that we can at most achieve a square root distance. So we're not going to be able to break the Polylog square root n barrier. So what Hastings-O'Donnell observed, and actually this idea is also present in this earlier paper by Friedman, Meyer, and Luo, is that we can introduce twists, in some sense, to increase the distance. So going back to this toric code example, so here on the left-hand side, I've drawn a torus, so the opposite sides are identified. However, I have kind of performed a twist in the middle. And in the toric code, all that you have to know is that the distance is given by the shortest non-contractible loop. So if you have an L by L torus, then the distance is simply L. By performing this twist, I have actually increased the length of one of these loops. So for a non-contractible loop to kind of go around the torus, the twist kind of introduces a detour that the loop has to make to kind of close up on itself. Okay, so these twists can be described in the language of fiber bundles, which are objects which are at home in differential geometry. And these are described in terms of a base manifold, and then a fiber manifold, and local data which describes the twists. And what Hastings, Haar, and O'Donnell show is that if they take a random code as the base, and they take a circle as a fiber, so by circle I always mean a repetition code, and they just kind of introduce random twists between the fibers, then they achieve a distance scaling as n to the 3/5 up to polylogs with high probability. Okay, let me be slightly less vague. So the base code, let's say, has n prime bits. And the fiber is a repetition code, which we choose as of the same length as the base code. And the twists have to kind of go along length of square root of L. Then the total code has n prime squared qubits. So the idea here being, again, like this, I'm trying to make this very intuitive. So we just took a product between the base code, which is just this disk, and we take a fiber, which introduces the z direction. So these things just multiply. The encoded degrees of freedom are simply given through the base code. And since the base code can be a good code, this can scale with n prime. And what they then show, and I unfortunately can't give you a good intuition for this because this is based on probabilistic arguments, is that the x distance scales with square root of L times n prime. So this gives us a distance scaling as n to the 3/4 with high probability. And that distance essentially scales with L. So this means we get a distance of n to the 1/2. Okay, but as you can see, we are still limited by the z distance. So if the distances are different, we agree that we take the lower one. So we are kind of still limited in this case. So what they do is they perform another product, And this product is taken together with a classical code. So as an input, we take a quantum code with some parameters. We take a classical code, and we obtain a quantum code where, again, the size just is given by the product of the codes. The encoded bits or qubits are just given by the product of the encoded qubits and the encoded bits. And the distances either stay the same or they multiply. And again, an intuitive picture here is if you're familiar with the surface code, we could just take a surface code which is imbalanced, meaning we have, say, one distance is much larger than the other distance. Then we can just take a product again. We obtain a three-dimensional version of the surface code, and one of the logical operators will become sheet-like, and the other operator essentially kind of stays the same. And yeah, using this trick, we can kind of balance out between the two distances. Okay, so now we observe that if the product of the x distance and the z distance scales faster than the square root of n, we can break the barrier. And in their example, this was exactly the case. So they obtain a code which has distance scaling with n to the 3/5. There's one caveat though. They have to assume that their random code has polylog check weight. So the resulting code will not be LDPC. So it will not have constant check weight. However, this can be fixed, but the issue here is that they have to introduce more qubits. So this is where this polylog factor comes from. Okay, so this brings us to lifted products. First of all, are there questions so far?
A quick question about the picture slides ago. So you have the random base code. Yeah, that one. So
yeah.
Where's the twist?
Oh, okay. So sorry. Yeah, I know brushed over this. So in black, I kind of show what the local structure is in the base code, and then in blue is what it looks like in the fiber bundle. So you can see that what used to be nearest neighbors in the base code now are kind of far apart in the fiber bundle, and this is exactly this twist of length square root of L. So in the product we kind of I know stretch out things which used to be local in the base code, and we kind of stretch them out all over the fiber. That's kind of the idea, and this is then kind of I know translates into this distance bound. And I hope I can kind of I know give you more intuition in the other product notions of where this kind of comes from. Okay. And again, please feel free to interrupt me at any point. Okay, so the second notion of products are the lifted products, and these are a bit more technical. So I will kind of try my best to highlight the main points. So the main idea is instead of taking the tensor product of classical codes just over F2 over these, so the tensor product of the classical codes, as I showed before, were these binary matrices. And instead of doing that, we substitute this by the product of an L-dimensional commutative algebra, which is binary. And the check matrices look the same. So these you've seen before. However, the entries are now entries in R. And in fact, we can kind of pull. So what this tensor product means is we can pull elements of R from one side to the other. And what this gives us is that the check matrices will be smaller by a factor of L, since the algebra elements in R can be represented. This is like an L-dimensional algebra, so they can be represented by L matrices. So this is where this factor of L roughly comes from. And we can consider a special case. So the special case is the F2 algebra, which is generated by a single element, which is of order L. So we just take this as the algebra, and as the second code, we just again take a repetition code of length L. So the checks are just generated by algebra elements 1 plus x. So you could think of this as just as the nearest neighbor checks, the nearest neighbor parity checks of the repetition code. And just again to kind of, I appreciate that this is quite technical, so just to kind of give you more intuition, the connection to Hastings-O'Donnell is that you can think as x as a shift operator along the fiber. So in fact, the object we construct is more or less exactly the same, just in a different language. There is a fiber which now is described by this algebra, and again there's a product with another code which is a random code, and similarly to the fiber bundle construction, we perform random lifts of this base code, and this will give us random twists. And by doing so, there's slightly more structure than in the Hastings-O'Donnell work. So they actually avoid this problem of weight reduction. And so what I should have said was that this base code that they consider is constructed from a special type of graph, so expander graphs, which have been featured in earlier talks. And a result that they use is that we can perform random cyclic lifts. This is a result by Agarwal and others. And by doing so, we still can preserve the expansion properties of this graph. So now they do something more extreme than in the Hastings-O'Donnell case. They take, again, this classical code of length n prime as a base code. However, they choose the fiber to be exponentially large in the size of the base code. So now they obtain a quantum code. Again, the sizes just multiply. And the problem here is that, again, the degrees of freedom that we encode are just determined by the number of degrees of freedom we can encode in the base code, which is only logarithmic. However, they have a very elegant averaging trick. And with this trick, they can show that the distance scales linearly with L. So this is how they get the almost linear distance. So this is like the most extreme example. However, they also show that there is another technique which is similar to the distance balancing, which they call dimension balancing. And the idea is they take further normal tensor products of their code, of their quantum code, with classical codes whose parameters we can control very easily. And by performing this product, we get a new code. And since we can control the parameters of the classical code very easily, we can kind of make a trade-off between the distance of the code and the number of encoded qubits. So they introduce this parameter alpha, which is between 0 and 1, and we can essentially interpolate along this line of how we want to have, like how we want to choose our number of encoded qubits versus their protection, aka the distance. Okay, so this brings us to the third example, which are balance product quantum codes. These also are based on two classical codes as inputs. However, they also come with we assume that they come with an associated symmetry group. And abstract idea here is we can take just simply the normal tensor product of the classical codes and then perform a symmetry reduction. And in fact, this idea is already present in this more algebraic language in the lifted products. And yeah, the outcome is a quantum code, but with reduced number of physical qubits. So the symmetry reduction reduces the number of physical qubits. However, it leaves the other properties more or less invariant. Okay, so this brings us to the question of how we can obtain symmetrical codes. And I'm sure many of you already know this, but for those who don't, the ingredients are expander graphs, which are a certain type of graphs which have a very strong connectivity property. And this connectivity property is measured by the Cheeger constant, which is simply given by the following ratio. So we take some subset of vertices and we look at del S. So this is just the number of edges which connect vertices inside the set S with vertices outside the set S. And we look at the ratio of the size of this set with the size of S. And if this is very large, then we have a good expander. So for example, if we look at a complete graph, then this is a very good expander. However, this graph is an example of a very bad expander, since we can just take all vertices on the, let's say, left-hand side, and there's only a single edge connecting to the right-hand side. And for reasons that will become clear in a moment, we were interested in expander graphs of constant degree. So I should say that Hastings-O'Donnell and Panteleev and Kalachev in the fiber bundle and the lifted product codes paper both use expander graphs. And they essentially use random graphs, which turn out to be very good expanders. However, our motivation, or partial motivation, was that we wanted to have an explicit, meaning non-random construction. It turns out that if we just take graphs which kind of nicely embed in hyperbolic space, then these tend to be very good expanders. In fact, there's a celebrated result due to Lubotsky, Phillips, and Zanak, who show that optimal expanders can be achieved in this way. And these are Calligraphs of the two groups, either PGL or PSL. And in fact, these can be kind of thought of as hyperbolic tessellations, which I will kind of do in this talk. Okay, so the other ingredients are kind of turning expander graphs into codes. Comes from Zipser and Spielman, and they show that we can combine families of expander graphs with local block codes, just meaning small local codes of constant size, and we can use these ingredients to obtain families of good classical codes. So let me give you a little fun example. So even for those of you who are familiar with this, I hope this is kind of fun. The idea, or the example that I'm showing you, is essentially a graph which is embedded on a surface of genus 3. So you can kind of see it rotating in the upper right-hand corner. And the surface is tessellated by triangles, giving rise to this degree 7 graph. And I want to define a classical code on this, but I will do it different from what people in the quantum community might think. So I don't want to kind of define a parity checks in terms of putting qubits on the edges and then measuring the parity of all qubits belonging to of all edges belonging to a single vertex. But what I want to do is I want to measure or kind of constrain the edges around a vertex to become code words of a local code. And in my example, I will consider the 743 Hamming code. So you can see on the lower right-hand side all code words up to cyclic permutations of the Hamming code, because this is a cyclic code. Okay, so let's say I want to do this, then and let's say we want to kind of see what a code word of this code looks like. Then let's start at some vertex. Let's start at the one in the middle, and let's ensure that there is a code word around this vertex. So if the edge is grayed out, it has a 0, and if it has a thick line, it has a 1. So I'll just take this highlighted code word in the lower right-hand corner around this vertex. And now you see that since the Hamming code is a distance 3 code, the vertices at the other endpoints cannot be satisfied. So there are certainly checks which pick up on this. So I can try to fix this. So I can kind of try to build up a code word by doing this iteratively. So you can kind of think of this as some sort of Sudoku. I will try to kind of fix, try to satisfy the checks locally by just building up larger and larger code words. And you can see that due to the expansion of the graph and the distance of the code, they kind of force me to kind of build up larger and larger, to kind of put in more and more thick edges into this picture. So again, the expansion of the graph and the distance of the local code kind of conspire against me and force me to kind of build code words of weight of order of the size of the total graph. So here are just all the code words of this code. So sorry, this is just a basis set. So this code encodes 12 bits. And by counting degrees of freedom, I can also show that when I kind of do this, I always also get a linear rate. So I hope this kind of example convinces you of the general procedure that's laid out by Sipser and Spielman, is that by using expanders and local codes, we can create classical codes explicitly with good parameters. Okay, so this is the ingredient that we use for the balance product. And again, I want to kind of retreat to the topological notion, given that I always have I can always kind of treat this code into so I can always kind of embed this code on the surface, so I can kind of speak about topology. And balance products already exist in topology. So let's say I have two topological spaces, X and Y, and I have a group acting on both spaces from the left and from the right, respectively. Then we can define an anti-diagonal action on the Cartesian product of these two spaces. Yeah, by just taking the usual Cartesian product and then factoring out this anti-diagonal action, we get a new topological space, and this space is called the balance product. Okay. And yeah, similarly to Hastings, O'Donnell, and Panteleev and Kalachev, we take products with repetition codes. So we take an expander code, which exhibits some cyclic symmetry, a repetition code, and the symmetry group itself. And just to kind of, again, give you some geometric intuition, because I appreciate this is a slightly technical definition. Again, our expander codes come with some hyperbolic Riemann surfaces, in which they embed nicely. And you can take the surface and you can just wrap it around itself. So a little bit like how you would store socks in a drawer, you just kind of wrap them around themselves. And then we glue in these circles in terms of repetition code, which are the repetition codes. So this is kind of like the geometric picture. And yeah, just for the experts, so people who are more familiar with let's say with the homological description, what we actually deal with is it's called a double complex. And in this double complex, our checks are defined through boundary operators. And just what I want to kind of very quickly say here is in this double complex, the top left and the top right are our qubits, and top left and bottom right are the checks. And these differentials kind of give us our checks. And here highlighted is just the differential of the expander code itself. So what this shows is that the qubits essentially see the checks of the expander code, or in the more geometric intuitive picture is we just have like this large surface on which lives the expander code, and all the qubits in the surface essentially only see the checks of this expander code. And from this, I get ahead of myself. From this, you can kind of intuit, I hope, that one of the distances will in fact be linear in the total size of the system. Okay, so let me not dwell too much on the ingredients here, but just to kind of again give some intuition of where the parameters come from. So we define our expander codes using the Lubotsky, Phillips, and Zander construction. So that means we look at Calligraphs of PGL over a finite field. So the order of the finite field kind of determines the size of the graph, and it also determines the size of the cyclic symmetry, which is always present. So we can kind of prove that there's always a cyclic symmetry group of size q, and the total size of the graph scales like q to the 3. And we can always guarantee that these local codes, which also have to kind of fulfill some technical condition that I didn't mention, we can guarantee that these two exist using a slight generalization of a result due to Gilbert and Washamov. So just to kind of show you the properties of the codes that we get, the number of qubits scales with the size of the graph, of course. The number of logical scales as n to the 2/3. And then, as I just kind of mentioned a minute ago, the z distance is in fact linear in the system size. Again, you should kind of think of this as just one large classical code wrapped around itself, and this is why the z distance is linear. The x distance, on the other hand, comes from this cyclic fiber that we kind of glued in, and this unfortunately always has size 1/3 if we use PGL. So this kind of comes from this fact that we have q to the 3 here and q here. And then we can again take this, do this distance balancing procedure by taking a product with a suitable classical code, and we obtain k as n to the 4/5 and d scaling as n to the 3/5. Okay, we can kind of maybe try different groups here, but to get different parameters, but we haven't found any. Okay, let me just kind of quickly skip through this example because I'm kind of running out of time. So just because I want to show you that actually you can construct these codes and they're not too crazy. So essentially kind of taking the same example as I showed you before, we can obtain an example which has 546 physical qubits. It has 6 logical qubits, and using some Monte Carlo brute force, we can upper bound the distances. The x distance is exactly what we would expect because our fiber has distance 13, so this is exactly what we get, and that distance is 18, and the checks are also not too large, so they are of weight 6 and 4 to 8 for the z checks. So it's just to show you that we can kind of quite easily kind of get like small examples, and actually this kind of scales quite favorably compared to the surface code. Okay, so the last point I want to make is we have these 3 examples of products. However, the balanced product is a bit different in the sense that it's somewhat more general. in the sense that the fiber is not restricted to be anything like a circle or a torus, as it is the case for the other construction. In the language of lifted products, you can say that the associated group algebra, which I didn't say this very clearly, but we can have, I know, describe the lifted products in terms of the balance product, and then there's a group algebra associated to the balance product, and this group algebra doesn't have to be commutative. So this leads us to a conjecture, and this conjecture is that we can use balance products to actually build good LDPC quantum codes. And the idea here is that we just take two suitable classical codes with suitable symmetry groups acting on it. And by performing the balance product on both of them, so instead of taking one good code and one repetition code, we just take two good codes. And by doing this, we obtain a good LDPC quantum code. And in fact, we can already prove that the encoding rate is linear. So what's left here is, of course, the hard part, which is the distance. Okay, so I'm kind of running out of time. So there were a few things that I didn't talk about. One of them is all this can be cast in the language of homology, which is quite natural. It streamlines a lot of concepts, and it makes proof simpler. And just a shameless plug, if you want to know more about the background and kind of understand a little bit more of the technical results without kind of diving into the three papers, you can check out this perspective article that I wrote with the co-author. So thank you very much for your attention, and I'm happy to take any questions.
Time for one or two questions. So there's one in the Q&A. Let me see. In the balance product code, the linear distance is for a slightly different notion of distance, right? I.e. the subsystem code.
Oh, right. Yeah. So there's like a technicality. So I can kind of know. So it's not for a different notion of distance. So we were quite careful about this. Oh, Jesus. Right. So in this picture, you can kind of see it. So there's a technical problem where the expander code might have the parity checks might have linear dependencies, which lead to qubits which lead to logical operators which have low weight. So this doesn't have to be the case, but we have no proof that this. Well, we have no construction that kind of excludes this case. However, we can kind of remove we can safely remove these logical degrees of freedom and just kind of declare them gauge degrees of freedom. But again, I want to kind of stress that this is not for a different notion of distance. It's still the true distance. You just have to be very careful that you can't just kind of multiply a logical operator with a gauge operator, which could potentially reduce the distance of the product. And yeah, this is something you have to be kind of, careful about. Yeah.
Any other questions? All right. Well, let's thank Nikolas again and all of the speakers in the session.